ASML's real EUV machine is roughly the size of a school bus. China just activated one that needed an entire factory floor to fit inside. Same job, same light, 15 times the space. And the reason for that size difference tells you almost everything you need to know about where this technology race actually stands right now. Picture that contrast for a second, because the numbers alone don't quite capture it. Walk into a room built to hold a single school bus, and picture ASML's machine parked comfortably inside it. Doors closed, nothing wasted. Now picture an entire factory floor, wall to wall, needed just to fit the Chinese version doing the same job. That's not a small design difference. That's the physical footprint of a problem nobody outside a handful of engineers in the Netherlands and Germany has ever fully solved before. Here's the question that should already be forming in your head. If ASML spent 2 decades shrinking this machine down to something that fits on a truck, why would China build one that's this much bigger? Is that a sign of failure? Or is it something else entirely? Stick around, because the answer connects to a number most coverage of this story completely leaves out. And it's the number that actually decides whether this machine ever makes a real chip. Let's start with what actually got activated, because the word matters here. Inside a sealed compound in Shenzhen, a team completed this machine in early 2025, and it's been running tests ever since. It successfully generates real extreme ultraviolet light, the exact wavelength needed to print the world's most advanced chips, by firing lasers at molten tin droplets tens of thousands of times a second, creating plasma hotter than 200,000 degrees Celsius in the process. That part works. It genuinely works. But here's the sentence that changes everything about how excited you should be. It has not produced a single working chip. Let that specific gap sit for a moment because it's easy to rush past it. Generating light and manufacturing a chip sound like they should be close to the same milestone. They're not. Generating the light proves the physics works. Turning that light into a usable, defect-free chip over and over, thousands of times a day, reliably enough to sell, is an entirely separate engineering mountain, one that sits on the other side of everything we're about to walk through. So why the size then, if the light itself already works? This is where the domino actually falls. ASML's engineers spent years compressing this exact process into an incredibly tight, compact footprint, because every extra centimeter of distance the light has to travel means more energy lost, more precision required, more things that can go wrong. China's team reportedly tried to match that same compact design first, and failed. So instead of solving the compression problem, they solved a different one. They made the whole system bigger, giving the light more room to work with, essentially trading elegance for raw output. That's not necessarily a dead end. It's a different engineering bet entirely, one that prioritizes getting something working now over getting something small later. Think of it like 2 different ways of winning the same race. One runner spends years perfecting their form, shaving off wasted movement until every stride is as efficient as physically possible. The other runner never quite masters that form, so they compensate by simply running longer, harder, using more raw energy to cover the same distance. Both runners can technically finish. Only one of them is actually sustainable over the long haul, and right now, it's genuinely unclear which category China's approach falls into. Here's the team behind that bet, and it's a genuinely strange story on its own. The project pulled in former ASML engineers directly, recruited through a campaign that started back in 2019, offering signing bonuses between 3 and 5 million yuan along with housing subsidies. One of them, a scientist named Lin Nan, previously ran light source technology inside ASML itself. Some naturalized citizens living abroad were reportedly issued Chinese passports specifically to bring them back for this project, despite China's official ban on dual citizenship. People close to the program have compared the entire effort to a Manhattan Project, and separately, a research institute in Changchun called CAOMP has been offering PhD researchers uncapped salaries and grants up to 4 million yuan, specifically, to work on replacing the components China couldn't source any other way. Think about what that recruitment strategy actually reveals about the entire approach here. This wasn't a program that assumed China's own universities could independently reinvent 30 years of accumulated expertise from a standing start. It was a program built on the premise that the fastest way to close a knowledge gap is to go get the specific people who already carry that knowledge in their heads and pay whatever it takes to bring them home. That's a fundamentally different strategy than pure domestic research, and it's exactly why this story moved as fast as it did. That last detail is worth pausing on, because it raises the exact question the next part of this video answers. What components, specifically, does China still need to replace, and how many of them are we actually talking about? Here's the number that puts this entire story in real perspective, and it's the one almost no coverage of this actually leads with. According to an analysis published this year by 3 Chinese semiconductor executives themselves, in Science and Technology Daily, ASML's real EUV machine contains roughly 100,000 individual components, sourced from 5,000 different suppliers around the world. Their own words for it were that ASML mostly just serves as the integrator. Sit with that for a second, because it reframes everything you've heard about this story so far. This was never really a single company's secret. It's an entire global industrial ecosystem, 5,000 specialized suppliers deep, that ASML happens to sit at the center of, coordinating rather than single-handedly inventing every single piece. Call this the integrator problem, because that's genuinely the clearest way to think about what China is actually up against here. It's not one locked vault that opens the moment you find the right key. It's 5,000 separate locked doors, spread across a dozen countries, each one guarded by a different specialized company that spent decades becoming the only reliable source for its own tiny piece of the puzzle. Reverse engineering. The machine ASML assembles is one problem. Reverse engineering the 5,000 companies that feed into it is a completely different scale of problem entirely. That changes what China's team is actually up against. It's not one hard problem to solve. It's 5,000 separate relationships, 5,000 specialized manufacturing capabilities that took decades to build and refine, all of which need some kind of domestic equivalent before a factory floor-sized prototype becomes a genuine production tool. Here's what that actually costs, in real terms. A single one of ASML's finished machines sells for around $250 million. Not because of one expensive part, but because of everything that has to come together perfectly across that entire 5,000 supplier network, tested, verified, and integrated into one working system. China's version, according to multiple accounts, is still missing some of the highest precision components. Specifically, the ultra-precise optics, normally supplied exclusively by the German company Carl Zeiss. Chinese institutes have been working on domestic replacements for exactly that piece. But as of the most recent reporting, the optical system inside this machine still needs major refinement before it can reliably do the one job that actually matters: printing a usable chip. Notice the pattern here too, because it keeps repeating throughout this entire story. Every time China's team solves one piece of this puzzle, whether it's the light source, the recruitment pipeline, or the raw funding, the next piece waiting behind it turns out to be just as hard, sometimes harder. The optics gap is simply the current version of that pattern, and there's no strong reason to assume it's the last one either. Now here's the part of this story that genuinely surprised me, and it's not coming from a Western skeptic with an obvious reason to downplay China's progress. It's coming from inside China itself. That same March 2026 analysis, written by 3 Chinese semiconductor executives who understand this industry as well as anyone alive, explicitly warned against reading this prototype as evidence the technology gap is closing quickly. And a separate assessment from the US-based think tank CSIS added a specific pointed caution of its own, noting that Chinese local governments, universities, and firms all carry strong incentives to exaggerate their own progress on a story this politically valuable. That detail deserves real weight, because it's a genuinely different kind of source than what most coverage of this story relies on. It's easy to dismiss American or European skepticism about a Chinese breakthrough as simple rivalry. It's a lot harder to dismiss the exact engineers and executives working inside China's own semiconductor industry, publishing in a state-affiliated outlet, choosing to caution their own audience against overreading the exact headline you're watching a video about right now. That's the honest scorecard, and it cuts both directions at once. What's true? The light genuinely works, and that alone is a real verified engineering achievement that most Western analysts didn't expect this soon. What's also true? The size, the missing optics, and the still unrefined precision all point toward a machine that's closer to a proof of concept than a production tool. And even the Chinese experts closest to this exact project are telling their own audience not to get ahead of the actual timeline. And what is that actual timeline? Sources close to the project have told Reuters that Beijing's official target is chip production by 2028. But that 2030 is considered the more realistic milestone internally. Here's why even that number deserves a second look, though. By 2030, ASML and its customers like TSMC aren't expected to still be running today's standard EUV machines. They're expected to be a full generation ahead already, on high-NA EUV systems built for the chip nodes coming after this one. Which means even in the best-case scenario, where China hits its own 2030 target exactly on schedule, it's not catching up to where ASML is today. It's catching up to where ASML already was, while the actual frontier keeps moving somewhere else entirely. It's worth naming that pattern too, because it's the single biggest reason this specific technology race behaves differently than most others. Call it the moving finish line problem. In most competitions, catching up to where a leader currently stands actually means something. Here, the leader isn't standing still waiting to be caught. Every year China spends closing today's gap is a year ASML spends opening a new one on the next generation of hardware, which means the real target for China's engineers isn't fixed at all. It's a number that keeps recalculating itself while they work. Think about what that actually means for the size of this machine one more time, because it brings the whole story back around to where we started. A factory floor-size prototype that took this much recruitment, this much money, and this much reverse engineering just to generate light still has to shrink down, still has to source thousands of missing components, and still has to catch up to a target that won't stop moving while it does. That's not a small ask. It's arguably a harder problem than the one this specific machine just solved. Watch whether China's next version actually gets smaller, because a shrinking footprint is the single clearest sign that the underlying precision problem is genuinely getting solved, rather than just being brute-forced around with extra size and extra power. Watch the ZEISS optics gap specifically, since multiple sources point to that exact piece as the harder remaining wall compared to the light source itself. And watch whether more of those 5,000 supplier relationships start getting replaced by domestic Chinese alternatives one at a time, because that number, not the headline about activation, is the real scoreboard this entire race is actually being played on. There's a broader lesson sitting inside this specific story too, one that applies well beyond just this one machine. Genuinely hard technology monopolies rarely get broken by a single dramatic breakthrough. They get eroded piece by piece, supplier by supplier, over years of unglamorous, expensive, incremental work that rarely makes for a satisfying headline on its own. A factory floor-sized machine that generates real light but no real chips isn't the ending of that story. It's closer to the opening chapter, and whether the chapters that follow move quickly or slowly depends entirely on how fast those 5,000 missing pieces actually get replaced, one supplier at a time. Drop one word right now, before this video ends. Massive. If you think a factory floor-size machine that actually generates real EUV light is a genuine turning point, size be damned. Mirage. If you think this is exactly the kind of story China's own experts just warned you not to overread. Type it now, then go watch exactly how close the laser inside this same machine actually is to matching ASML's real output, because that number tells a very different story than the size of the room it's sitting in.